Okay, good morning, everyone. Let's get started. We'll wrap up chapter 1 today. We'll do a brief review of some circuit analysis techniques, probably from a year ago. How many of you still remember Thevenin and Norton? Kind of? That's good, because we'll be using that a whole bunch. All right, let's see. Okay, so we stopped here, right? Notations. AC and DC signals. Comprised. Okay. All right, so I wanted to say, just to recap, if it's all uppercase, all capital letters, it's DC. If it's all lowercase, it's AC. And if it's a mix, lowercase notation and uppercase subscript, then it is AC signal plus DC component. Okay. That gives it the total signal. Now, the reason we do that is, of course, because we'll be studying diodes and transistor circuits where you'd have DC bias voltages, and then you'd apply an AC signal on top of it. Okay. And so you have to pay attention to the notations when you calculate the voltages. Same thing with the labs. As an example, we would represent, let's say, perhaps a total signal as 3 plus, I don't know, cos omega t, right? Any component in a signal that has a variable, meaning it's a function of time, the value of that quantity changes as a function of time, means it's AC. So this component right here would be referring to an AC signal, and this, which is a pure number, would be a DC. Make sense, right? It's pure numbers, 3 or 5.4, 0.198, any number, but does not have any variable, meaning it is not a function of time. The value is constant, and it's DC. If it is a variable, then it's an AC. So if you look at a signal and it has multiple components, whether it's a fixed number, constant value versus a variable. Make sense? Right? Now, there was a homework posted yesterday, it's due tonight, but apparently there was some sort of glitch in the sync between the Connect and the Canvas system, so it did not deploy for a few hours, and I didn't realize that. There was supposed to be a sign in the morning itself. But anyway, several students did see it. So if you have not yet seen it, it's a short, very small homework. Shouldn't take longer than 15 minutes. But the deadline is tonight. And if you do get stuck, let me know. If you're running late, let me know, and I'll give you an extension. Right? Okay. So from here, let's look into sources. This is something that you already looked at it, so I'm going to just do a quick review. Sources are of two kinds, voltage and current. In real life, in reality, they are one and the same thing. You cannot have a voltage source without it supplying current. You cannot have a current source without it supplying voltage, right? When you actually use a benchtop supply, any kind of power supply for that matter, it's supplying both voltage and current. So the difference is that a voltage source is a device that would supply a constant value of the voltage, and the current is variable. So the current will adjust, or the power supply will adjust the current depending on the needs of the load circuit that is connected to the power supply. Again, a voltage source supplies a fixed or constant value of the voltage. Applies to both AC and DC. We are not talking about with respect to time, okay, in this case. We're just talking about voltage versus current. As an example, if you have a 10-volt source, actually, let's keep it simple. 1-volt source and you connect a 1 ohm resistor to that power supply, what do you expect the current to be? Right? Ohm's law, 1 amp. If you connect a 10 ohm resistor to that same source, what is the voltage and what is the current? Voltage will still remain 1. Current is adjusted and gives you 0.1. So depending on what load you connect, the current will be adjusted. And hence that is referred to as a voltage source. Voltage source simply means constant voltage mode. So if you have noticed, when you use the DC power supplies in the labs, anywhere in this building or anywhere else for that matter, it'll have a small tiny notation saying CV. And that stands for constant voltage. So it's the power supply is running in constant voltage mode. And because it adjusts the current depending on the requirements of the load, we have to set a current limit. Sounds familiar, right? Same thing for a current source. Current source is the exact same unit, but now you run it in constant current mode, and the voltage is now adjusted and variable. The power supply automatically adjusts the voltage depending on the needs of the load. So if you have a 1 amp source and you connect a 1 ohm resistor, your voltage would be 1 volt. If you connect a 10 ohm resistor, constant current source, constant current mode will still supply 1 amp. The voltage is now adjusted to 10 volts. And it's one and the same thing. All right, 10-second pause. Let me know if you have any questions. For those of you attending online, just feel free to speak up because I would not be able to monitor the chat window. Good? All right. Difference between these two. If it's a circle, it's independent source. If it's a diamond, it's dependent. And of course, plus and minus refers to the voltage. Arrow through the source means it's a current source. So these two are independent sources. Let's draw a line right there. Okay. Independent and dependent sources. The reason we have dependent sources is because they're very useful in modeling, especially for this class and going forward, obviously. Semiconductor device electronics, as I stated on the first day, we use a lot of different models to analyze our device behavior or to describe our device behavior. And several models will incorporate a dependent source. Okay. Simply put, a dependent source will supply its rated voltage or current, but it depends on some other part, some other quantity in a different other part of the circuit. It could be as simple as a voltage divider network. Like a voltage divider network will supply a specific voltage at one point in that circuit, but it depends on an actual power supply for its output. Let me explain with an example. If you have a voltage divider network or voltage divider circuit, let's say all of these are 1 kilo ohm or any equal value to keep things simple. And you apply 3 volts here. What is the output at X And what is the output at Y? With a reference to ground right here. Anyone? Y would be equal to 1 volt, X is 2 volts, divided in 3 equal parts, right? With respect to ground. So plus, minus, and plus, minus. X is dependent on its value from this power supply voltage. Vs is equal to 3 volts. If Vs changes to 6 volts, X changes to 4. And Y changes to 2 volts. So it supplies a constant value. It is behaving like a voltage supply. The points X and point Y are behaving like a voltage supply, but that output at X and Y are dependent on the actual source Vs. So you can model points X and Y as a dependent voltage source that is dependent on another quantity. Okay, this is just one simple example, but when we get to diodes, when we get to transistors, we would simply use a model without actually knowing what, there is no physical quantity like a resistor in there. We are simply using a mathematical model, if you will, to describe the behavior of the device. Okay, so they're very useful in that sense. Also, the dependency can be on both voltage and current. So a voltage source could depend on voltage or current, and the current source could also be dependent on voltage or current. Do you all remember those terms, perhaps, from last time, from a year ago? So this would be so this is a voltage source, right? This is a voltage source, and this is a current source. Let me use CCT, current source. That's my acronym for current, CCT. That's what I grew up learning. And voltage was VTG. Okay, so if you come across some unfamiliar terms, sometimes I'm so used to using them over decades, just feel free to ask, right? So this on the left would be classified as a voltage controlled voltage source or a current controlled voltage source. And this would be a voltage controlled current source. And this would be a current controlled current source. Okay. So the first C is for control, second one is for current. So again, dependent sources can be of 4 kinds: voltage controlled voltage source, current controlled current voltage source, and then voltage controlled current source and current controlled current source. These are terms that you should just be familiar with when we actually get to analysis. Things progress at a faster pace. And so sometimes we won't have time to stop. So I just want to do a brief review at a slightly slower pace in the first week. Any questions? Yes. Okay, so the question being asked is, does it relate anything to do with the current limit or the voltage limit we set on the power supplies? No, that's just the real life power supply. When we perform theoretical analysis here, everything is ideal. And so if it's a voltage supply, we would simply say, okay, if it's a current source, we could connect like a 0.1 ohm to like a 10 amp source, and it would say it's like 1,000 volts or 100 volts or something that's coming out. Realistically speaking, that's not, we could perhaps design something like that to work, but that's not something we'll encounter. So the answer would be no. Okay, speech. All right, so This is also there in the book, and this is also something that I'm fond of using from, again, from several years. Your approach to analysis should always be like this. First, you would want to just read the problem statement, extract as much information as you can from the given information. And especially for electrical engineers, a lot of the information would be in the circuit diagram. It would also be given in either a timing diagram or a graphical description of a voltage or a current. Okay, I'll give you an example. So read the problem statement, understand the problem statement, understand the problem statement, and then extract as much information as you can from the given information. Apologize, my allergies are making it really worse at this time of the year. It's just a random circuit. Sometimes we have circuit diagrams with values imprinted directly in the circuit diagram. Can anyone still understand me? And so when I say extract information, you're looking at each and every component in the circuit diagram, even down to the smallest detail. Okay. So the source value would be written on there, plus the current limit. All of that could affect the circuit in multiple ways. All right. You might calculate a current somewhere in the circuit that could be above 1 milliamp, let's say 1.5, right? If you get a result of 1.5 somewhere in that circuit and you miss the current limit, your answer is incorrect, right? If the power supply can only supply maximum of 1 milliamp, your answers anywhere in the circuit cannot be more than 1 milliamp. Does that make sense? Right? So if you miss that, you would have done everything correctly. Your approach would be correct, your methods would be correct, your analysis would be correct, your calculation would be correct, but your final answer would be incorrect because of this tiny detail. And so when I state extract as much information as you can, that is what I'm referring to. Also, and I've made this mistake often, not recently though, but I've made this mistake. If you have a graphical description of a quantity like a voltage or current, right? T, units of T, usually seconds. But sometimes we have unit prefixes in there. Sometimes it's milliseconds or even microseconds. Oh, by the way, that Greek letter mu, this is basically the Greek letter mu. That's what we use for micro. So again, that's what I use for micro. So the mistake I have made often is not paying attention to the unit prefix. And I've done the entire solution with like milliseconds when the time scale was in microseconds. So again, that's another part where I would say, you want to pay attention. And then of course the units on the Y scale too. So your approach as an engineer should always be first read and understand the problem statement. That's the absolute first. And extract as much information as you can from the given statement. Then you define your unknowns. What is it that you're trying to find? voltage across the capacitor, current through the inductor, output voltage at the end of the circuit. So you define your unknowns, make any assumptions that you need, right? Oftentimes, we do not have all the information given to us. So we often make certain assumptions. We modify the circuit in certain ways, which we'll look at when we do Thevenin and Norton. And then once we note the assumptions, outline approach is okay. Sometimes I'm in a rush and I tend to just skip through those, perform your analysis. And once you perform your analysis, you need to verify your results and see if they match your assumptions. Remember, I said it's an iterative process. So you would have to actually make an assumption, perform your analysis, look at your solutions, and see if your assumptions are valid. If they're not valid, you try a different analysis technique and you do it all over again. And you keep doing it in a loop until you get the right answer. Okay. And then, of course, we also perform computer simulations and theoretical hand calculations. Okay. V equals IR, you could use Ohm's law, calculate, or you could use perhaps P-Spice or LT-Spice to simulate your circuit so you would know what your answers should look like. All right, 10-second pause. Let me know if you have any questions. Any questions from anyone? Okay. It's time, 8:32. All right. This is also this slide. Reasonable numbers is something that I just actually spoke about, right? You have to be cognizant of the power supply voltage limits and current limits. Your power supply is only supplying 10 volts. You would not be able to have more than that power supply voltage anywhere in the circuit. With given exceptions, okay? We look at clamper circuits in, when you get to diodes in chapter 3. There it is possible to have voltages that could be larger than the supply voltage. Because, well, going ahead, supply comes, goes to a capacitor, capacitor stores the energy, negative half cycle, the capacitor energy plus the next half cycle adds up together to give you a larger voltage. So those are some minor exceptions, but in general, if you are analyzing a circuit, it is not possible to have more than what the power supply is supplying in general. And then, of course, the same thing for the current range, AC signal limits. We'll look at that when you do transistor amplification. You would also have seen that, if you remember, when you performed op-amp analysis, right? Op-amps have infinite gain. If you create an inverting and non-inverting amplifier with a gain of, let's say, 100, apply 1 volt, do you expect to get 100 volts at the output? Yes and no. Yes, if the DC supply voltage is in excess of 100 volts, you would get that at the output. But the energy cannot come from thin air. If your power supply to the op-amp is only 10 volts, doesn't matter what the op-amp gain is, the maximum you can obtain is 10 volts. And so that's what is meant by AC signal limits, right? So AC signal can also not be more than your DC biasing voltages, and any voltage or current in the circuit cannot be more than the source or supply voltage. So all three of these kind of in the same category. Not more than the energy source with a few exceptions. like clamper circuits. Okay. And then calculate component values. You also have like tolerances for resistors, capacitor values. In theoretical circuit analysis, everything is ideal, meaning a 10 ohm resistor will have a 10 ohm value. In real life, the 10 ohm could be 10.01 or 9.99, right? So there is a minor variation in there. Yes. Oh, clamper circuits. Let me, yeah, clamper circuits. So it's a diode circuit where you would, we have applied DC offset voltages to AC signals in function generators in the lab. So clamper circuit does something like that. You take your AC signal that's at the 0 level and it adds a DC component to it. So you can either shift it up or you can shift it down. And so if you use a capacitor absorbs the energy in one half cycle, and the other half cycle that absorbed energy is added on to that AC signal, which behaves like a DC component. So it clamps the output at a certain level and hence called a clamper circuit. But that's later on in chapter 3. So for one final thing about the calculated component values, typically theoretical values can be anything, right? Unlike actual physical components. So theoretical values could be, you might obtain 1 milliohm, let's say, right? 1 milliohm resistance. Theoretically, it's possible. But if you are actually looking at your circuit, depending on the source, depending on the circuit configuration, you might sometimes obtain like fantastical values, like maybe kiloamps, perhaps, or it might be, I don't know, micro ohms, right? So when we say pay attention to the component values, the results that you obtain, that would be some nonsensical or fantastical values like these, that should give you pause that probably my analysis might be incorrect and I need to recheck my work. Okay. And that's the point of that point. All right. Any questions before I move on? Okay. Oh, sorry. All right. So you learned circuit analysis in 113, 211, and 212. It seems like you learned whole different range of analysis techniques, right? But everything that you learn is right here, is based on these 3 equations, and that's it. Everything that you need to solve a circuit is right here on this slide. Ohm's law, KVL, and KCL. That's it. These are the 3 laws that you need to know, and everything else is derived from these 3 laws, right? Ohm's law is basically V equals IR. KVL is you sum up the voltages around the loop. Sum of voltages is equal to 0. And KCL is all currents through a node should sum up to 0. And that's it. We take these 3 equations and we combine them in multiple ways, and we create new analysis techniques. But everything that we need to solve a circuit or any kind of circuit is Ohm's law, KVL, and KCL. That's what all the entire circuit analysis is built on. Now, I'm assuming everyone has their own favorite way of applying KVL or KCL. KCL is rather straightforward. For me, all I do is I take all the currents entering a node equals to all the currents leaving a node. And that's it. That's the easiest way that I know of, and that's what I use. KVL can be applied 2 or 3 different ways. Some students have learned some techniques in physics before they come to college. And so I let them, like, if you're comfortable with something, then just stick with it. You don't have to, do what I do. So I'm assuming at this point, everybody's comfortable applying KVL in their own manner. If not, you let me know and I'll be happy to explain it, but we'll do it outside of class. All right. Okay, so people remember voltage division, current division, fully, right? It's an example, but voltage division, again, derived from Ohm's law. Simply stated, when you apply a single voltage across a series combination of resistors, a fraction of that supply voltage appears across each resistor. And that fraction is given by the ratio of the resistor to Req. So total equivalent resistance would simply be R1 plus R2 plus R3 plus R4. That's your total equivalent resistance in this circuit between the outer terminals, which is as seen by the voltage source. And because we are applying one voltage to a series connection of resistor, a fraction of that total voltage will appear across each resistor. And that means VR1, voltage across R1 should be a fraction of V total. I'm just going to write VT. Okay, VT. And a fraction is given by the resistance or the ratio of the resistance to Req. Okay. I hope this rings some bells or rings a bell, right? The reason we go over this is because when we actually get to the circuits and we perform analysis, you'd have to do this quickly and efficiently and more importantly, correctly. Okay. So VR4 in that same sense would be V total times R4 over Req. So that's voltage division. Obviously, current in a series circuit is going to remain the same. Current is equal, there's only one pathway for it to flow through, so it's the same through all four resistors. All right, any questions? Okay, current division. How about current division? What's the equation for current division? You remember from the top of your head? It's the same as the voltage division, except the ratio is now flipped. So Req in this case is the reciprocal of the sum of the reciprocals. Right? It's parallel resistors. When you have components in parallel, the voltages are all the same. Same two nodes, same voltage. But the current gets divided. And when the current gets divided, a fraction of the current goes through each parallel path. So Req is the sum, the reciprocal of the sum of the reciprocals of the resistors. And then I1 would be a fraction of the total current Is, and the fraction is given by the ratio of Req to R1. Okay. I2 similarly would be Is times Req over R2, and R3 again, Req over R3. So again, this is derived from Ohm's law. It's a two-step derivation. Again, as a refresher, you should be able to quickly and efficiently apply voltage and current division. Make sense? One thing I'd like to point out, this is a little bit of a tangent. If you have a series connection of resistors, what is the Req? The sum, right? See, 10 plus 10 plus 10 plus 10, or 10 plus 30 plus 60, right? So 100 ohms if they're connected in series. What is the REQ of this parallel connection? 1 over 10, 1 over 30, 1 over 60, and then you take the reciprocal. Here's how the human brain works. When we are adding stuff together, it's simple. We know that if we add 1 plus 1, the resulting value will be larger than 1. Or if we are adding 60 plus 30 plus 10, 100 is larger than the largest value in that series network. Our brains automatically recognizes, we don't have to think about it. But if it's a parallel connection, then the resulting value will always be smaller than the smallest resistor in that parallel connection. So if you do REQ for 10, 30, and 60, your resulting value should always be less than 10. If it's higher than 10, then your answer is incorrect somewhere. Okay, and that's something that we don't directly think about. But that's, again, another key thing to keep in mind. If it's a parallel network of resistors, the resulting REQ will always be smaller than the smallest value in that parallel network. All right, so let's move to the most important topic, Thevenin and Norton equivalent circuits. Leon Charles Thevenin was a French telegraph engineer during World War II. He postulated a theory and stated that if you have a linear network comprising of sources and resistors and other components, we could theoretically represent that entire large circuit as one single voltage source in series with one single resistance. So it doesn't matter how many components that circuit has, you could represent it with only two. This circuit right there. So you could have a large circuit comprising of multiple resistors, multiple voltage sources, current sources, and you can simplify it and represent it as one single voltage source and one single resistance between the output terminals. In this case, the output terminals are right here. Okay, and R6. So the example I use is, when I teach those classes is you're trying to find a value for R6. So instead of doing multiple analyses, all you wish to do is you remove R6 from your analysis and you analyze the rest of the circuit without R6. And you can represent that between these terminals. The minus and plus doesn't mean anything right now. It's just a notation that I'm using. V out plus, V out minus. Okay. So Thevenin theorem is basically voltage source in series with a resistor. And then a few decades later, there was a American researcher working at, I want to say Bell Labs, by the name of Edward Norton, not the actor. He's not that old. And he postulated his own theory based off of Thevenin's theorem, where he said that you could take the exact same circuit and represent it as a current source in parallel with the resistance, or in parallel with the same resistance. And that came to be known as the Norton theorem. Okay. And obviously, Ohm's law connects the three. V equals IR, Thevenin voltage, is equal to Norton current times the Thevenin resistance. There is no new analysis technique in Thevenin and Norton. Everything's still the same. The only thing is the setup of the problem. Do you all recall the setup of the problem? Perhaps. Let's do a quick recap anyway. So you have this circuit, right? You have that circuit. All you have to do for Thevenin voltage is you take your output terminals. If there's a component connected there, perhaps you might want to remove that. So you remove R6 here and analyze the circuit and determine V out at those terminals. Okay, so you remove R6 and you perform an analysis to determine V out between those output terminals. And that V out is your Thevenin voltage. So the circuit would look like this. You have R1, R2, R3. You don't have to draw this out. This is just, illustration purposes. And then R5, voltage source, and minus and plus. Did I get everything? 1, 2, 3, 4, 5, 5, current source. Yep. And that's your V out. R6 is removed. And that V out is your Thevenin voltage. Okay. Let's see, 9 minutes left. What do you do for Thevenin resistance? Well, not, that is correct, but we do not short, that is correct. But the more accurate term would be, we would, turn off the voltage source, but we would actually remove and replace the voltage sources with a short circuit. So yes, the answer is correct, but we don't short the voltage sources as much as replace them with a short circuit. What do we do with the current sources? We replace them with an open circuit. Absolutely. So you all remember your stuff, which is very good. And then you simply measure the REQ between those same terminals, and that gives you your RTH. In the lab, of course, it's very simple. You have a circuit, you turn on the power supplies, you measure the voltage at the output, done. That's your Thevenin voltage. And then you replace it with this. Again, put your multimeter to the same terminal, switch the mode to measure resistance, RTH, done. So the calculations might take you like 40, 45 minutes, maybe an hour, depending on how big the circuit is. But the actual measurements takes like less than 2 minutes. What do we do for Norton current? We go back to the original circuit with all the sources. And now, because current needs a pathway to flow through, we place a short circuit wire between our output terminals. And the short circuit wire is your Norton current, IN. Okay, so that's the setup of the circuit. Once you have this setup, then you analyze using any technique you want. The Ohm's law might work if it's a smaller circuit, KVL, KCL, node voltage analysis, mesh current analysis, any technique you want. Node voltage and mesh current analysis are a combination of Ohm's law and KCL and Ohm's law and KVL. There's no other new analysis technique in there. Right? Let's take a 10-second pause. Let me know if you have any questions regarding these. Any questions? Okay, so then we go to an example with dependent sources, because that is what we're going to work with, a lot of these models. The dependent sources, obviously, well, if you, again, I keep harping back to like 1 year ago, if you recall, independent sources can be reduced to zero, meaning replaced with a short circuit and open circuit. But dependent sources, diamond sources, cannot be reduced to zero. Okay, they will have their own value in the quantity, so you cannot reduce them to zero. And so dependent sources, you simply have to treat as a quantity in your equation. And that's all. And so if you have a model like this, which again, in a diode and a transistor, we will have models like these. This model has a dependent current source, right? It's a dependent current source, and it depends on I1. So it is a current controlled current source, CCCS, right? You see, the value of this is beta I1, right? It's beta I1. So it depends on I1 to supply its rated current. Beta value is already given to us. Whether it's given or not given is irrelevant. The point is, when we write our equations, we have to take that current into account as any other current quantity. Okay, so if you want to solve this for Thevenin voltage, we would want to find V out, VO, right? If you want to find the voltage at any point in the circuit, you start applying your equations. If it was a simple circuit, I would apply this Ohm's law. I can perform mesh current analysis, or I can perform node voltage analysis. You can take your pick. Mesh current would require you to assume a couple of mesh currents. Node voltages requires you to assume a reference node. Typically, we choose the negative end of the power supply as our reference node, and then we perform our analysis. Okay. So if I want to find VO, that VO is the same as the voltage across that 1 kilo ohm resistor, right? And so let me make an assumption that the current is flowing in this direction. This is coming up. This is coming from left to right. So if I apply KCL at the top node, I get, what do I get? I1 plus beta I1 plus, let's call this IS. Okay, let me remove this mesh currents. Is equal to IS. Right, two currents entering, one leaving. And so I1 plus beta I1 is equal to IS. You simply plug in. Now it's node voltage analysis. So you represent each current in terms of the node voltages. And here the voltage is, VI. And here it's VO. And so I1 is going to be VI minus VO divided by R1 plus beta IB. And so this would be VI minus VO over R1. And then IS would simply be VO minus 0 divided by RS. So let me go over each one of those quantities. I1 is flowing from left to right, right? It's flowing from left to right. Current is like any other physical quantity, always goes from high to low. Okay, pressure always flows from high to low. Temperature always goes from high to low. Current always also goes from high to low. Conversely, if current is going from one direction to the other direction, it's going from left to right, we are stating that the left node is higher in electric potential than the right node. So arrow is going this way. So VI must be higher than VO. So it's VI minus VO divided by R1. And then VO minus 0 divided by RS, because that current is flowing down. At this point, you plug in all the known values. You know the values of R1 and RS. VI is known. The only unknown is VO. We solve for VO. That is our Thevenin voltage. Solve for VO. And that is your Thevenin voltage. I think we are almost out of time. Does that make sense? Right? So just to recap, if you have a dependent source, whether it's voltage source or whether it's current source, you simply use it as a quantity in your equation and you eliminate the unknowns. Take any analysis, choose any analysis technique you prefer, and you solve using, you write equations using that technique and you solve for that unknown quantity. This is an example from the book. I can't remember exactly. It's 1.4 or 1.5. So please review that example and reach out to me if you have any questions. Quiz 1 will be on Monday, the first 15 or 20 minutes of class. You can take the quiz in person or you can take it online. It's open book, open notes, open internet, but no dial a friend. Okay, so if you are taking it online, you must have cameras on for the duration of the quiz. And then once you finish, the work time would be either 15 minutes or 20 minutes. Once you finish the quiz, there'll be 5 extra minutes for students to scan and upload their work on Canvas. You can use a tablet and you can simply just upload it, upload that, upload your work. Yes. Sorry, what? The question being asked is whether the quiz will resemble the material done in class. It'll be a little bit of both, but lean towards the homework assignments. So I believe basically, we teach during the week, and then students do the homework assignments, and then the problems would be similar to the homework assignments. So again, review this example. This is an example from the book. Please review it and reach out to me if you have any questions. I will be available all through the weekend, okay? So I'm always available via email. But if I'm out and about somewhere, doing chores or, shopping or whatever, it'll be a while before I can get to my, laptop, but I can always answer emails, okay? Yes. So R Thevenin, you would place, the question being asked is about R Thevenin. You would place with a dependent source at the output, we would place a voltage source or some sort of energy source. And then you solve. So you'd have Vx or Vs, and then you'd have current flowing through because of that voltage source. And then your R Thevenin would be this V over I. Any value we wish, yeah, could be any value. All right, we'll end class here today. I'll see you all on Monday. Again, if you have any questions, feel free to reach out.